recording. There, session's being recorded. Fantastic. Loud and clear, good stuff. Thank you. So, welcome to the last lecture of 161. You made it, all 12 of you here. Before anything, obviously you're aware that the final exam is available now, but I will not be answering specific questions regarding the final exam during this lecture because I want to cover a little bit more material. But if you have a high-level question about the exam, you can ask it now, but no specifics about the exam itself. So feel free to ask that question. If you do, just type it in the chat. But a couple of things before we get going. So yesterday's lecture, we talked a little about models of computation and how, it was kind of funny to look at strings and patterns in strings to kind of represent complexity of certain things. But, we saw an example of a finite state machine that can generate at least one A followed by some arbitrarily large number of A's, an infinite number of A's, followed by a B, or vice versa. We saw a thing that did that. But then we also saw a system that can generate palindromes, strings that are the same forward and backwards or symmetrical. To be clear, I suppose the one that we defined was only even-length palindromes. But we could easily modify it. I'll come to that in just 2 seconds. Yeah, we can easily modify that system that we defined, those systems of rules, to also include odd number palindromes as well. And then the last one, which no one had any ideas for, and here's hoping you played around with it, but that will generate all strings of some number of A's, followed by some number of B's, followed by some number of C's, where the sum number is the same amount. So like A, B, C, A, B, B, C, C, A, B, 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 C, 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 and so on. And that system, those strings couldn't be generated with the less powerful system of computing. And the palindromes couldn't be generated with a finite state machine. So, it was kind of neat. And in today's lecture, we're going to talk a little bit about recursion. And we've looked at recursion a little bit already in the course. We played around with it. And I'm going to show you some neat algorithms with recursion. But what's really cool about recursion is kind of like a natural thing. It's kind of hard to explain, I suppose. And I'm not trying to be like philosophical or anything, but of course, if I give you a set of instructions and tell you like, okay, there's a loop and execute the loop so many times, like, you can do that. It's what the rules are. But it's kind of funny. Like if we define a formal system where we can define functions like we do, we can like call functions from within themselves. That's totally allowable within this system. And that's like where recursion comes up. So it's I don't know, it's just this like fundamental property of these formal systems in our universe, which is kind of neat. But anyways, if at the end of today's lecture, or even after yesterday's lecture, you're kind of curious about this stuff, and maybe you are going to be a computer science student, or maybe you've taken the class, you've learned a bunch, and you're like, well, that's exciting, but I don't really have time to fit it in. Okay. But if you think that's just particularly interesting and you want to learn a little bit more, I actually really recommend getting your hands on this book. It's called Gödel, Escher, Bach. It's not a light read, I'll admit, but it's written in such a way that it's accessible. You don't need to be a computer scientist to understand this. It won a Pulitzer Prize a number of years ago, so it's written to be accessible. I do highly recommend the book because it'll kind of give you a sense more into what the hell computer science really is. What else? Well, I guess I'll answer the question. What exactly is the difference between a notebook file and a .py file? Okay, so a .py file is like the Python script. Usually when I'm writing scripts and whatnot, like if you open a .py file, if it's done correctly, you open it in like Notepad or something, you'll just see a whole bunch of code in there. Where a notebook file is like, it's got the code in it, but it's also formatted it such that, you know, kind of like the IPython notebooks that, like in Colab, where, you know, you've got the cells with some code in it, with cells below with code in it. You can have text in those notebooks as well. So the IPython notebook is kind of like a super Python file. That it's like the Python code, but it also includes all the extra stuff that the notebooks give you. So in a .ipynb versus a py, you can get the py files from the IPython notebook file. So hopefully that's helpful. Okay, I suppose I'll start by sharing the screen. Super duper Python file extravaganza. Yes, that is the, I don't think it's the technical word they use, but it's something along those lines, yeah. Actually, I suppose before I jump into that, are there any final questions about anything related to the semester that we can maybe talk about right now before we jump into it? Because, you know, everything from last week or so was like extra. So we could take a moment to maybe go into specific questions that anyone has. I realize those questions might take a while to ask, so feel free to raise your hand and don't turn on your mic and we can talk about it. Or if you want to type it in, feel free to start typing. But in the meantime, I suppose I'll start going over the content. But if I hear a little boop with a question, I'll come to the question and see what we can do. So I will start sharing my screen. Okay. We're going to talk about recursion. And we're going to look at a couple of cool, whoa, haha, recursion. A couple of cool little, whoop, no, we're not going to look there yet. Oh my goodness, there we go. Nope, there we go. Okay, recursion and more sorting with recursion. Okay, so we kind of saw something like this before. Here's a function called fact. It takes n, presumably n is an integer. If n is 1, return 1. Otherwise, return n times whatever fact n minus 1 is. And it looks weird, right? Like what stands out to you? Well, I mean, the function, the definition of this function makes a call to the function. Do you see, like, this right here is the function definition. We are telling Python, okay, here's a function. It's called fact. You know, it takes an integer. It's got these rules. But you'll also notice that within the function, within the definition of a function, there is a call to the function. So the function definition requires that it exists, which is weird, right? It almost sounds like paradoxical, I guess, but it's not. It checks out. So the function is defined in terms of itself, which is weird, but it checks out. So like, let's do a quick test. Actually, I already copied it over. We've got this. I hit run. 120. Why? Well, I'm going to open up some text here, and let's think. The first time I call fact, I'm asking that, right? But then I go inside, and then it's like, okay, does so n is 5, right? Is 5 equal to 1? No. Then we're going to return n, which is 5, times fact of n minus 1. Well, that's 4. Then we go, now we're like inside fact 4. And okay, is 4 equal to n? No. So we go down, pardon me, is 4 equal to 1? No. So then we go down and we say, okay, well, it's 4, return 4 times fact of 3. Okay. So we go in there and we ask, okay, is, wait, 1, 2, 3, 4, there. Is 3 equal to 1? No. So we go down and we say, okay, well, return n, which is now 3, times of 2. Is 2 equal to 1? No. So we go down another time, return whatever 2 times the result of fact 1 is. Now we go down here, and I ask the question, okay, what is the answer to fact 1? Well, is 1 equal to 1? Yes, it is. So, I mean, this is easy. Great. Return 1. Done. So this returns 1. So you'll kind of see that like we went down, right? So we asked, okay, fact 5, but in order to know the answer to fact 5, I needed to know the answer to fact 4. And in order to know the answer to fact 4, I needed to know the answer to fact 3. And in order to know the answer to fact 3, I needed to know the answer to fact 2. And in order to know the answer to fact 2, I needed to know the answer to fact 1. And then, wait, I actually just knew the answer to fact 1. Fact 1 was like a statement. Fact 1 is like, okay, if n is 1, it's that. It's just 1. Great. So now I know the answer to fact 1. And because I know the answer to fact 1, I now know the answer to fact 2 because it's 2 times 1. And 2 times 1 is 2. So I know the answer to fact 2 because it's 2. Thus, I know the answer of fact 3 because fact 3 is 3 times fact 2, which is just, 6. Then fact 4, well, that's just 4 times fact 3. Fact 3 is 6, so 4 times 6 is what? 24? 6, 12, 18, 24. Perfect. 24. And then fact 5, well, that's 5 times what fact 4 was, and we know that fact 4 was 24, so 5 times fact 4, well, that's 120. So, like, we had to, like, go down, get an answer to, like, that simpler version of the question, and then we can go back up. So it's kind of like when I asked fact 5, I had a lot of delegation taking place. I like, what's the answer to fact 5? Like, imagine I asked one of you in the room. Let's go back over here and see if we can make this example work. Typically, I do this. If this is a lecture hall, this is a lot easier to do. But here, I don't know, maybe we can get this to work. Raise your hand if you have a mic that works and are willing to participate. Work with me here. It's the last lecture. Oh, come on. One person. 2 people. Leave your hands up. I want to see if we get a sufficient number of people. I know all of you have mics. They're like built into your computers. Come on. 3. Come on. A couple more. I need like 2 more. Oh, come on. It's going to be a really boring lecture if we don't get some participation. It's the best way to learn this stuff. Well, I guess we'll do a simpler version where we'll ask what fact 3 is. Wait, leave your hands up just so I know. And then also turn your mics on. So let's say, like, we're aware of what that function says. If n equals 1, return 1. Otherwise, it is n times whatever fact n minus 1 is. Okay, so let's say we start with Thomas. Okay, Thomas. So let's say I ask you what fact 3 is. All right? But you don't know because n's not 1. So you don't know what factorial 3 is. But if you knew what factorial 2 was, you could answer it. But you don't know what it is. So how about this? You're going to find someone who could answer the question what factorial 2 is. And then they're going to get back to you. You're going to ask them, they're going to figure it out, and then they're going to get back to you to tell you what the answer to fact 2 is. And once you know the answer to fact 2, you can answer what fact 3 is. Okay, so how about this? Thomas, I'm going to ask you what fact 3 is, and then you're going to ask someone what fact 2 is in order for you to answer my question. Sound good? So what's fact 3?
Josie, what's fact 2?
Scout, what's fact 1?
It's 1. Maybe the mic's not working. Maybe they thought they had a mic, but they don't. He is fact. Well, can you hear me? No, we could not. And it looks like she got disconnected. So we can't hear you, but maybe just type the answer then. 1, exactly. So now you tell 1 to Josie. So now Josie, with that information, you could calculate what fact 2 is, right? It's n, which is 2 times 1, which is, of course, what?
So fact 2 is 2?
Exactly. So tell that to it's actually Cole, right? Not Thomas. Is that right?
Yep.
Okay. Tell that to Cole.
Cole, fact 2 is 2.
Perfect. So now, Cole, you know what you now are capable of telling me what fact 3 is, right?
Fact 3 is 6.
Yeah, because it's just, well, 3 times what fact 2 is, which you now know. So it's like you're delegating this question. You know, like, oh, you know, you ask me what fact n is. I don't know, but it's n times whatever fact n minus 1 is. I don't know what n minus 1 is. I don't care. I'm going to ask someone else to calculate what fact n minus 1 is. Then they'll get back to me, and then I can answer my question. But I'm going to delegate it. This is a classic, simple, introductory example of what recursion is. Now, recursion has a bit of a bad rep, especially for intro computer science. People love to say that, oh, but you can put your hands down, by the way. People love to say like, oh, it's so complicated, it's scary, everyone's terrified of recursion. No, I don't think that that's true at all. It's weird. It kind of requires you to flip a switch to think slightly differently. But it's not weird. It just follows all the rules. You have a function that just calls another function. And just as long as you follow the rules, you're good to go. Now, let me ask you a question. Let's say just a quick little quiz. So, of course, we saw that, let's wait for the screen to actually start sharing. We saw that, you know, in the definition of fact, in fact, we had this like case here, like a point where we knew the answer, where the answer to the question wasn't related to the definition of itself. Like this, like if n is 1, it's 1. That's it. We often call this the base case. Then down here, we have like the recursive case, the recursive step, where the answer to the question is defined in terms of itself. So this base case is important because it's kind of like when we were working our way down, we hit that floor, which was like when n is 1, and then we were able to go back up. What do you think would happen if I do this? Just get rid of that base case, and it's just there. What do you think? Just take a second, think about it. What's going to happen? I'm going to hit run. Let's see. Uh-oh. Maximum recursion depth exceeded. It might be hard to see what happens, so let's print out what n is in this. My goodness, what actually happened here? Page up. Okay, yeah. So, okay, it started at 5. And then in order to answer, well, it's 5 times fact of n minus 1. So we call the function where n is 4, then 3, and then 2, then 1, then 0, then -1, then -2, -3. It had no bottom. It's effectively an infinite loop. It'll run forever. I mean, it's technically, I guess, it crashed on us, right? It said, no, maximum recursion depth reached. So it looks like the computer was like, we've got infinite recursion, let's just stop running. Great, and in fact, it looks like it ran a total of 960 times, I guess, which is interesting, or 61. But, so it's kind of neat. Like, it looks like that base case is rather important. Anyways. Oh, then here's a fun little joke. What is it? If you know anything about recursion, you know not to order the combo platter. Or alternatively, maybe you do know to order the combo platter. I don't know. I'm going to zoom out so you can read it. Give you a second to appreciate the brilliance of this joke. If you don't get the joke, I'll explain it, which of course kind of ruins the joke. But so if you know anything about recursion, you know not to order the combo platter. So let's look at the combo platter. Combo platter includes all items with an asterisk. So that means the combo platter can include hand-breaded fresh mushrooms, hand-breaded fresh onion rings, ravioli, jalapeno poppers, cheese sticks, cheese balls, and and a combo platter, which of course includes hand-breaded fresh mushrooms, hand breaded fresh onion rings, ravioli, jalapeno poppers, cheese sticks, cheese balls, and of course it also includes a combo platter because combo platter has an asterisk, and so on and so on and so on. A rather silly joke, but there you go. I'd like a combo platter with my combo platter. Yes, it also seems like a great way to get an infinite amount of food. I wonder if that would hold up in any situation, but whatever. So, okay, don't panic. I'm going to talk about two big world hunger. I know, right? They just need to understand what the formal system is, and then we're good to go. So the next two algorithms I'm going to show you, quicksort and merge sort, are based on recursion. If I'm explaining it to you, and at any point you're like, wait, I'm lost, what? Don't worry. It's, again, not on the test. These are advanced ideas. They're complex. But they're recursively defined, and they are based on very, 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 very simple ideas. So let's start with quicksort. It's a sorting algorithm that is, on average, going to be way better than the other sorting algorithms we talked about last Friday, I think. Friday and Wednesday, I believe. Way faster. And the weird thing is, I mean, it's not intuitive, like, it's not intuitive, but it's probably not a sorting algorithm any of you have used before, despite being way better, despite being well known among, you know, people that run algorithms and whatnot, who design algorithms and everything. I'm willing to bet you haven't, you've never used this before. So here's the high level ideas. There's two key things you have to understand before we can talk about quicksort. And these two ideas, let's call it 2.5 ideas, are very simple. And you're going to understand them, I promise you. The first 1.5 ideas is, if I have a list that is either empty or has one thing in it, that list is sorted, right? It is. If there's nothing in a list, at the very least we could say it's not sorted. So it's sorted, right? If we have an empty list, there's nothing out of order, it's a sorted list. And if we have a list that has one thing in it, it's a sorted list. It's only one thing. It feels kind of silly, right? But it's still a sorted list. Do you agree with that idea? Raise your hand if you take exception to that idea, and then we can talk through it. Well, seeing nothing, I'll assume that we're all A-okay with an empty list or a list with one thing in it is an already sorted list. Nothing needs to be done. Put that list in order. The next thing we need to understand is, if I take a sorted thing, like imagine I have a sorted list that has all values less than some number x, where x, who cares what it is? But all the numbers in this list are less than x, and that list is already sorted. Don't ask me how it's sorted, just it's already sorted. And I have another list where with all values that are greater than or perhaps equal to, if we want to include duplicates, but we have another list of all values that are greater than x. And that list is also sorted. Don't ask me how we sorted it, it's already sorted. Would you agree that if I took the list of values that are smaller than x, that are already sorted, appended to that list x, and then appended the sorted list of things that are bigger than x, we would have a bigger sorted list? The thing. What do we see? The order combo platter, some sense pointer combo platter. Yeah, okay. But is ordering the combo platter in some sense a pointer to the combo platter inside the combo platter? Yeah, it's like self-referential. But back to the quicksort. So I've got a list over here. It's sorted. It's all less than some arbitrary value that we've got here. And I've got a list over here that's already sorted, but these values are all bigger than this arbitrary value. If I take this list, put it there, put this list here, this new list is still sorted. Presumably it's bigger, and it's sorted. Do we agree with that statement? Raise your hand if you agree. Keep it up. I want to see. Because if you don't agree, ask why. Like ask me a question because clearly it's not clear if only two people are okay with it. I'll say it again just to be super, super safe. I have a list. It's already sorted. Do not worry about how it got sorted. Here's a list. It's already sorted. And it just so happens that all of these values, pretend my face is a value. All of these values happen to be less than my face. All of these values are bigger than my face. This, it's already sorted. This is already sorted. If I do this, it's still sorted, right? If I put all these things together, it's still sorted. It must be the case. Cool. So with these two ideas, 2.5, because we'll say the empty list and a list of size 1 is sorted. With these ideas, we can very, 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 very easily sort a list way faster than the other sorting algorithms. Here's what we do. Here's how we do it. Actually, let me go back to the code that I give is not that great at making it clear. So here's what I do. I give you some list. You can call it whatever you want. It's just a list, and the elements in here, they're not sorted. I mean, maybe they are, whatever, but pretend they're not sorted. If that list has 1 or no elements in it, then it's sorted, actually. We're done. There's nothing to do. Do you agree with that statement? Why? Well, because by this fact, an empty list or a list with one thing in it is already sorted. So if we happen to get a list of size 0 or 1, it's already sorted. We're done. Just return that list, done. Otherwise, pick some element from that list. We'll call this element, this is the X. We'll call it the pivot, okay? So I've got some in list. It's not size 0 or 1. So let's pretend it's size n, where n is some arbitrarily large number. I pick a pivot. Let's say, I don't know, it's 104. It's just some value. And then I'm going to go through this list, in list, whatever we want to call it. I'm calling mine in list. I'm going to go and do a linear search through that list. But I mean, it's not even a really linear search. I'm just going to put my finger on each value in that list. And what I'll do is I'll go through this list of size n, taking all of the values that happen to be less than the pivot and put them in a list over here. And this list isn't going to be sorted, right? It's just I'm putting them over there. Just pretend I'm putting them like a bag. I'm just piling them up over there. But I'm also going to take all the values that are greater than or equal to the pivot over here. They're not sorted though. It's just I've got two piles of values that happen to be sorted. These are less than the pivot. These are bigger than the pivot, but they're not sorted, right? So they're just two piles of numbers. They happen to be less than and greater than the pivot. So here's the magic. Here's what we'll do. We'll just sort this list and sort this list and then put them together and we're done. That's it. Raise your hand if you're like, whoa, I've got a problem with what you just said. I feel like you skipped a couple of steps. Raise your hand if you feel that that's the case. I'll say this again just to be clear. I've got a list of size n. I arbitrarily pick some pivot value. I go through each of those n things, which will take n steps, right? I'll take each of those, I'll look at each of those n things. If that value happens to be less than the pivot, I just put it over here. I add it to this pile. If the value happens to be greater than or equal to the pivot, just put it over there in that pile. That's it. Then I've got these two piles. These are all less than, these are all greater than the pivot. All we have to do is sort them. And then by that second rule, all I have to do is say, like, well, take this list of sorted values that are less than me, this list of sorted values that are greater than me, and, you know, I'm good to go. That's it. That's the second rule. So raise your hand if you're like, yeah, you're skipping steps there, bud. Like you can't just, like you're just saying, oh, just sort those lists. I mean, that's kind of the problem, right? Like I'm saying, just sort it, but I'm supposed to be telling you how to sort it, and I'm saying, oh, just sort it though, within the definition of how to sort it. Seems strange, right? Well, let me put it this way. If I start with a list of size n. And let's say I get really lucky and I happen to pick a value that is like the median of all the numbers in this list of size n, okay? And I put all the numbers that are less than over here, all the numbers that are greater than over here. How big are these two things? How big is this one? How big is this one? If I happen to pick the median, someone type in the chat if you have an idea. If we started with of size n over 2, exactly. But I'm going to do this recursively. So now I'm going to call Quicksort on that list of size n over 2. I'm going to have to do that twice, once for this list and once for this sublist. But let's say I call Quicksort again on this sublist, happens to be size n over 2. Well, I'm going to pick that pivot again, and I'm going to have two smaller lists down here. What size will these smaller lists have relative to n? Someone type in the chat. N over 4. And if we were to do it again, what would we have? See if Scout can be 3 for 3. N over 8. Exactly. Looks like Cole, according to my records here, Cole beat you to the punch slightly. But n over 8, then n over 16, then n over 32, then 64, 128, and so on and so on and so on. Now, we can assume n is some finite number, and if we keep, you know, halving and halving and halving and halving, eventually I'm going to be left with fewer and fewer items until I have like 1 or 0, right? And then, well, once I get there, well, if the list is of size 1, it's already sorted. So all I have to do is take that sorted list and the other sorted list and put them together, and I have a sorted list. And then I cascade all the way back up. See, this is a lot easier to explain in person versus camera, but let's see if I can try to draw this. Let's do the whiteboard, actually. And please be good. So let's say I've got size n. Okay, that's my list. It's, you know, it's a list, right? Then I'm going to do like all the values less than n. I'm ignoring the pivot in this just for simplicity. I'm going to be left with a list of size n over 2. Let's make that blue. N over 2, n over 2. And their lists. Oops, nope. Then if I do that again, I'll have, nope, I want blue, and over 2, which of course is just 4. And we've got, you know, it's a list. And then let's see, can I select? No. How do I? Come on, I have to be able to copy or something. Geez, I should just be using Paint. Well, whatever. Dot, 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 dot. But then eventually, I'm going to run down to the situation where I'm left with, if we assume a nice power of 2, we'll be left with numbers of lists of size 1. If we keep dividing by 2, dividing by 2, dividing by 2, like dividing the list in half, I basically mean. Oop, that should be a 1, not a 2. And so on and so on and so on and so on and so on. So if this list of size n, now I know I technically have a pivot, which means it's actually like this is n over 2, n over 2 minus 1 or something, because we keep the pivot out. But let's ignore that for the simplicity of the analysis here. If we start with a list of size n, we have one list of size n. If we go all the way down to the bottom, how many lists of size 1 would we have? N. We've got n lists of size 1, because that's how arithmetic works. But, you know, these are sorted lists. Like, understand that the number in here is the number of elements in the list. It's not the value in the list, let's say. But we know this is sorted and this is sorted because lists of size 1 are sorted. And I know that these are less than these. So if I put these two things together, as I move back up, let's use a different number. As I go back up, this will be a list of size 2. But it's sorted because this is sorted and they're less than these values and these values are greater than these values. We put them together and it's sorted. But we know this is sorted, and if we have another one over here of size 2, because that's how it works, and I know these are sorted and less than these values, and these are sorted but greater than these values, well, I can, put them together and have a bigger sorted list of size 4. And all the way back up to the top. Isn't that crazy? So if you don't understand, that's fine. But if you do understand, I want to take a moment to talk a little bit about the analysis of this algorithm. Every layer, sometimes we call this idea like a tree. This is size n over 2, n over 2, n over 4, n over 4, n over 4. Notice that at each level, the total size has to add up to n though, right? We have 2 things of n over 2. We have 4 things of n over 4. We'd have 8 things of n over 8, and so on and so on and so on, until we have n things of size 1. The rows need to add up to n, or the layers. And the amount of work we have to do for each one, I mean, we have to we have to go through that list at the very top. We got to go through that list of size n, and we have to put our finger on each of those n things, and put the things that are smaller over here and the things that are bigger over there. So how much work is that? Well, that's n. That's like, if the size of the list is n, the number of things we have to look at is n. So for each layer, in order to put how many things are on each side, to put the things on the sides, we got to go through each of the n things. So that takes n steps. Then over here, we'd have to do n over 2 and n over 2 for a total of n things to put the things in the right side for each layer. So each layer we have to do n things. But now the question is, what is the depth of this tree? So we have to do n work for each layer in this tree. But now the question is, how many layers in this tree are there? I'll give you, someone type in the chat if you think you know. And you don't have to give me necessarily an answer that's a specific value, but you can tell me what the depth of the tree would be relative to the size of n. And I would be very happy if you could do that. So I'll turn, how do I stop this whiteboard? There we go. So while you think about that, I'm going to share my screen again to move on to merge sort, because sadly we're running out of time real quickly. You know what? I won't even move on to merge sort. I'll just move on. I'll just keep going. So merge sort, that's an even better one. It still has the basic idea of an empty list, or a list with one thing in it is already sorted, right? It uses that. But merge sort also works on this. We can merge 2 sorted lists together into a new, bigger sorted list really easily. You read this if you care. I'm going to move over. Yeah, there's merge sort. Self-reference is a really interesting thing. We saw we did this, right? So A is a list, and then we append to A a pointer to itself. So that list points to itself. And it's in these types of things where we get this self-reference where math gets weird, where programming gets weird. It's weird because you might feel recursion, it's still okay, maybe you get it, but it feels weird. You're normal if you feel that way. But we saw this example earlier in the semester. Is the following statement true or false? This statement is false. Well, so this statement here is referencing to itself. It's referring to itself. And this is somewhat of a problematic statement, because if this statement is false, I am not to believe what it says. Which means it's telling me that this statement is false. And if I am not to believe what this statement says, then if it's not false, it's true. So therefore, I should believe what this sentence says. So this statement is false. And if I am to believe what it says, well, if it's false, that means I shouldn't believe what it says, which would make it true, which means I should believe what it says, which means that I shouldn't believe, and so on. We've got a problem. Here's another one. You should say this to Pinocchio, his head will explode. What happens if Pinocchio says the following thing? My nose is going to grow now. Because Pinocchio's nose only grows when he lies. So if his nose in fact grows, that means he was telling the truth. Because he just told us that his nose was about to grow. Therefore, he was telling the truth. But if he's telling the truth, his nose shouldn't grow. That's another problem. Here's another classic, like easily understandable, more complex paradox. The Grelling-Nelson paradox. I particularly like this one. I'm going to give you two definitions, okay? An autological word is one that describes itself. And a heterological word is one, here, I'm going to stop sharing just because it's probably easier for me to just explain it. So autological words are those that describe themselves, and heterological are words that don't describe themselves. So this sounds weird, but it's not, right? Like, is English English? Yeah, it is. Like, English is an English word. Is unhyphenated, in fact, unhyphenated? Well, unhyphenated is a word that is unhyphenated, therefore it is autological. It describes itself. Pentasyllabic describes itself. The word pentasyllabic has 5 syllables, therefore it's pentasyllabic. But heterological words are ones that don't describe themselves, like the word hyphenated. The word hyphenated doesn't have a hyphen in it, therefore it's, it doesn't describe itself. A lot of words are not heterological. And if you want, you can go look up a whole bunch of heterological and autological words if you want. But if you're ever lost, the trick I always do is the word X, X? So like, is the word English, English? Is the word unhyphenated, unhyphenated? Is the word hyphenated, hyphenated? Is the word happy, happy? Probably not, right? Is the word computer, computer? I mean, that doesn't even make sense, right? So given that we've got these two categories, it seems reasonable to say that every word is either autological or heterological. That, to me, seems like a very reasonable assertion. Either the word is or is not autological or heterological, depending on which way you want to go. Raise your hand if you're with me so far. One person. Good. So all words are either autological, they describe themselves, or they do not describe themselves. Great. So it seems reasonable we categorize all these things, and I'm going to put them into two sets, set A and H. Set autological, set heterological. So if I ask you, where do we put the word round? Well, is the word round round? No, it's not. So I put that in set H, set heterological. Do we put the word writable in set A or H? Well, the word writable is in fact writable, so it's autological. So I should put it in set autological. Is the word harmless harmless? I suppose, it's probably, the word harmless probably hasn't harmed anyone. So I could put that in set autological. Now, where do I put the set autological? Does the word autological describe itself? Like, is autological autological? I mean, that's kind of a funny one, because maybe it's not that funny. If I am going to assert right now autological is autological, then it's autological. If it's not, it's not. So I guess it's just, this is up to me. Like, I just have to define, is autological autological? Does autological describe itself? Like, that feels kind of like a funny question, right? But I don't know, it doesn't seem too terrifying. It's just, it is or it isn't. It depends on the definition, I guess. Let's see, I hear a boop. What about bold? The actual word can be bolded and non-bolded. Well, it depends. Is it, can I do boldface? It doesn't let me use like markup. What? Oh. Whatever. Well, if so, okay. Autological was a funny one, but how about this? Where do we put the word heterological? This is where things get weird. So let's say for a moment that heterological is heterological. stay with me. Let's say heterological is in fact heterological. So that means, so let's start by saying the answer to this question is yes. If it is, the word describes itself. So is heterological heterological? Well, if it is, then heterological is describing itself. Therefore, it should go in set A, right? But if heterological does in fact describe itself, then it's not autological, it's heterological, because heterological is heterological. Okay, so is the word heterological heterological? If it's yes, then the word describes itself. Therefore, the word heterological must be heterological. What does it mean for a word to be heterological? It means it doesn't describe itself. Hold on. So either heterological, if heterological is heterological, then it doesn't describe itself. So does heterological not describe itself? Like, this is weird, right? So if it's autological, if the word heterological is heterological, that means it's autological. And if it's autological, it must therefore mean it's heterological. Because if it describes itself, its description of itself is that it doesn't describe itself. Let's go at it a different way. Let's assume it's heterological, where it doesn't in fact describe itself. So if it does not describe itself, then it means that the word doesn't describe itself. But that's the definition of the word heterological, which means heterological is heterological, therefore it's autological. Long story short, it looks like our plan to categorize all words into either set autological or set heterological is not possible. It seems as if that's something that can't actually be done, despite feeling like it should absolutely be capable. Like, we should be able to do that. It seems as if we can't do it. Need more categories? I mean, I suppose, but doesn't it feel like you shouldn't? It either is or isn't. But somehow we have something that is both and neither. It's weird, right? So this is a bit of a conundrum. And see, what's cool about this, and there's a lot more in this lecture that unfortunately, we run out of time in the semester, and if you're in computer science, this is stuff that we'll talk about a lot more in like third, fourth year. But what's cool about these ideas are, this isn't like a class where these things, this idea, this conundrum we have, if we have these are things that are fundamentally true about our universe. And these truths about our universe kind of require, I suppose, Schrodinger's cat, kind of like that, I guess. But it's like within our universe, there seems to be well-defined systems of rules that cannot possibly be all-encompassing. There's things that cannot be touched and described. It's impossible. There are some impossibilities within our universe. That idea of well, this statement is false. That is nonsense. I should be able to categorize every statement as true or false. I should be able to categorize every word as autological or heterological. If heterological is heterological, then it describes itself. And by it describing itself, it is asserting the fact that it's heterological. So if it's autological, it can't. If it's autological, it is therefore heterological. But if it's heterological, then it doesn't describe itself, which means that the word heterological doesn't describe itself, therefore it is autological. Oh my God. This is an interesting nuance about our universe, is that it seems as if that there are some unknowable things. anyways, I guess that's it for 161. Good luck on the exam. And is it possible our definition for illogical is up for change? Well, I mean, we can try to do that, but it's now we're like kind of playing a game of like, well, let's kind of like change the definitions here. It's just, this is kind of coming down to everything can either fall into one of these two categories. Like all statements are either true or false, but somehow this statement is false is neither and both at the same time. So it's not so much about focus, like we shouldn't focus too much on the heterological autological example. That's just an example highlighting these funny little paradoxes. But you're not crazy for thinking that. Like that's a good idea. But yeah, we won't focus too much on that. It's kind of more about like, well, it goes into class A or H. Long story short, 161 is over. Hopefully you learned a lot. Hopefully you feel compelled to take 162. If you're looking for something to do over the holiday break, which you probably aren't, I recommend watching the YouTube videos of 162 so you can get a sense of where we're going. Anyways, hopefully you learned stuff. I think you did. You learned to program, great. Otherwise, good luck on get your views up. Yeah. Please subscribe to my YouTube channel. All right. Smash like. Anyways, enjoy the rest of your day and good luck on your exams. Hopefully, see you 20. Thank you very much. Thanks for the course. I hope you enjoyed it. I hope you learned something. Even if you think you haven't, you did. You don't get this far without learning something. So enjoy and good luck on the exams. Hopefully my exam isn't too scary for you. It shouldn't be. All right, have a wonderful, wonderful break. Try to relax, enjoy it, and be safe.